thank Claudia for the invitation and introducing me, also Nicola and Shiro and everybody. So I think I should give a warning like Tina's talk. It will be more of a machine learning lecture. If you have prior ML knowledge, this will be probably helpful, I hope. But if you do not, then pay attention to the high level. And then you can look at the video and study at home. It's really more like a lecture in the beginning. And I'll talk about my work really at the end, because I need to prepare the scene to understand where I want to go and where I'm going, okay? So machine learning is well known for having many encrypted expressions, and I'll try to keep the machine learning language to a minimum, but if I fail, let me know, okay? So the roadmap is this, what we see, what users do, and what we are trying to predict. Then we'll see the different types of prediction, and I'll explain what they are, transductive and inductive learning. Then I'll try to explain what latent variable models are, what's an embedding, and how this relates to what I would describe as transductive learning. And then I will give a really brief, very quick introduction to deep learning, and how these different types of learning work with deep learning, what's deep learning, and what learning representations, and some of the shortcomings. And then at the end, I'll talk about deep learning for inductive learning. And then I'll talk about my work, so it will be quite all right. So I am daring because I'm going to talk about what a social network is like, and the behavior will be related to how I'm connected to the network. I will ask the social scientists to excuse me. It's a very computer science way of thinking. Okay, so just bear with me. So you can think of two sources of diversity in a network, right? Exogenous that my friends that you don't know are influencing me. Okay, my friends are influencing me, so my behavior is a function of what my friends are doing. Or you can think of an endogenous source of behavior that I have some intrinsic behavior, and my connections are related to this intrinsic behavior, and I behave like this no matter what. Okay, so just my intrinsic behavior. So in either case, we'll be using the user's position in the social network to predict its behavior. So in the endogenous, my network position, and I'm describing this very vaguely on purpose, determines how I'm influenced, right? So my position in the network determines how I'm influenced by other people in the network. If it's endogenous, then the network position indicates my behavior, right? Because that's how it came about to connect to other people. So I think the common goals in machine learning, and I think Tina did an excellent job describing this. We like predictions because predictions are measurable things. We can measure this, okay? So predicting labels in a network, right? For instance, predict my level of nerdiness, and that's very high. You can predict links, right? We want to predict missing links. I was warned that there was a missing link between this unknown figure here. So we want to predict that, right? So why machine learning will put so much emphasis on predictions? It's because we have a complaint here. He doesn't like prediction very much. Yeah, he's a social scientist. Okay, so prediction is a good way to test a model or hypothesis, right? It's a measurable, quantifiable way. As a computer scientist, I like that. All right? So that's why we are focusing more on prediction. Now, for me, like when you look at the structure, I will also look at other covariates, things that are like, for instance, node covariance would be I'm nerdy, I like mine and cheese, things that you can observe about me, right? These will be variables in your model also. And these observable variables can help determine other hidden variables, hidden behavior, like exogenous or endogenous behavior that I have. You can think of edge covariates like type of relationship, amount of communication, the words we use, and etc. as covariates on the edges, right? So they're node and edge covariates. Okay. Now, about model predictions and causality. Actually, we had a very interesting discussion at lunch, and it was not because I had made this slide before the discussion. Actually, I didn't talk about it. But there's a difference between predicting something and inferring its cause. And although I'm talking about endogenous and exogenous behaviors, I am not going to distinguish the two. Okay? Because to do that, you need causal inference, and I just want to predict something. So what is interesting, if you go read the Principia Mathematica, which is a very boring book, but extremely interesting, in book 1, definition 5, you find something that Newton said, that gravity, whatever it is, because he acknowledged that he didn't understand what gravity was, is a force by which bodies are drawn to each other, like magnets attract themselves, right? Or iron is attracted by a magnet. And that's all he needed to make predictions about planetary orbits. So he didn't know what caused gravity, but he was still able to make predictions. And we are going to do the same here. We are just making predictions without understanding what the underlying causes. Okay, so we will not disentangle the causes, but we can still make conditional predictions. Like if we see that the user friend did X, we can predict that the user will do Y, regardless if it's endogenous or exogenous. Okay. Okay, so now I'll talk a little bit about types of prediction. Transductive learning is the idea that I'm going to reason only about the specific examples that I'm given. Okay, so if you give me a network, I'm going to talk only about this network, the nodes that I see. So for instance, one assumption that I guess in networks we generally make without making explicit, as Tina pointed out, is that well-connected users have similar characteristics. For instance, the age of my friends can predict my age, right, or other things. It can be correlated or anti-correlated, but in any case, it will have some effect. My political affiliation can be related to my friend's political affiliation. But transductive learning will not learn general rules. It's learning something about those specific users related to their position in the network that you are given. When we talk about embeddings, we'll see that most embeddings are transductive methods. So inductive learning is the idea that we are looking for rules to apply over the entire data, even things that we have not seen yet. Okay, so we are given, let's say, a network, and we are trying to learn rules that we are given the rest of the network or another network, we can apply those rules to this other data. For instance, you can learn a rule that if half of my friends are nerdy, then, so if half of the friends of a user are nerdy, then the user is nerdy. So this is a general rule that you can then apply to another part of the network or another network. Okay, so this is the difference between transductive and inductive, right? So let's talk about then latent variable models. What's an embedding? I don't know have you guys heard of the word embedding being thrown around? Embeddings, embedding the nodes, embedding the behavior, right? Okay, so what is an embedding? So actually, a lot of the embeddings start with a network, surprisingly. And most embedding methods are transductive. But what's an embedding? Let's say, make it simple, let's talk about shopping recommendations, right? So these are the people shopping. I don't know why, but in the web you can only find pictures of men being bored by shopping and women being excited. Like I could not find them behaving the same way. Something to study. So now here we have the number of items that these users bought, right? And let's say I want to predict what they should be buying, right? So the items that they bought in the past, and I want to predict what they'll buy tomorrow, let's say. Or I want to recommend things to them. So this can be described as a link prediction problem on a bipartite network, right? So we have users and we have products. And Netflix and Amazon and all these recommendation systems that you hear about, most of them will have the same behavior. We have users, we have products, and then you have customer reviews, right? So each user will give a review for a given product, and then with this matrix here, you want to learn some behavior that then you can predict what they like and what they would dislike in the future. So how this is generally done is by embeddings. We want to have a low-dimensional representation, and Tina talked a little bit about that in her work. Actually, it's a lot about dimensionality reduction. So generally, the idea is to try to approximate this matrix that represents my bipartite graph, or my graph in general, my network, and also use network and graph interchangeably, like links and edges. Problem with computer scientists. So think of this as an adjacency matrix, right? So this is how much I like apricots, dried apricots. I don't like them. Okay? So I don't like them very much, so the color is very light here because I don't like them. Think about being bolder is I like more, and being lighter I like less. Then when I decompose, then what we'll do is to decompose this matrix into this factors, and the factors are just a mathematical way of trying to represent some intrinsic characteristics of the users. So here we have two factors, right? Rank 2 matrix. So this is what we call rank 2 approximation. And here on this coordinate here, we have all the users in your system, and these are all the products in the system. Okay? And each variable here is telling me in this latent characteristic, which doesn't have really an interpretation. It's just a way that the mathematics works. It will give me something, and then I'll try to interpret it later. So it kind of works the reverse way that you would want. So if you look at then at the products that it thinks are very strong in this latent representation, you would realize that this representation is for bitter things that are bitter, right? If it's bitter, then it's here. And these apricots are quite bitter. And if you think about the users, is how much they like bitter things. I don't like them. So when you multiply this value, which is a value small, by this value, which is large, you get a small value. So I don't like apricots because they are bitter also. But I like sweet things, but this product here is not sweet. So in the other representation where you would see that large values here are sweet products, right? You see that apricots are very light on that. They are very small values. While I'm very strong in sweet things because I usually buy sweet things. And then it learned that I like sweet things. And when you multiply the two, you get a small value. And then if you sum these two values that you get this value here, which is small. Meaning like I don't like. That's how it's representing this value here. It's trying to represent in what we call these latent coordinates. Okay? And this is what we are going to say is my embedding. Don't like bitter things, like sweet things. Okay? In practice, the interpretation is not as clear-cut as I'm saying. So if you go home and you try it out, don't blame me if you can't really understand what these latent representations are. It's not my fault. Okay? Not my fault. So mathematically, it works like this. I'm not going to describe it too much in details, but it's just, if you know outer product, this is the outer product between these two vectors, which gives me a rank 1 matrix. Now the product between these two vectors gives me another rank 1 matrix. I sum the two, and I get what my product, how much people like the product. Okay. So one example is singular value decomposition, but there are so many examples. So Tina was describing non-negative matrix factorization. There are like thousands of examples of this types of decomposition. They do, basically they're doing this that I'm describing, but in different ways, and they're assuming different models. If you think about modeling, they're assuming different models. Now, when I say my embedding is in the first coordinate, small value, second coordinate, large value. So this is my embedding. This is a point in this two-dimensional space. So the rank 2 approximation of my matrix gave me an embedding in two-dimensional space. Okay? Now, we have here, let's say, in the case of a network that's undirected. So what happens is that both of these coordinates are the same. These are the same things, okay? Because it's undirected. So here we have all the users, And here, again, we have the same vector as with all the users. And what these latent representations will generally show is some kind of community. It's not really community if you think about properly describing a community, but it's trying its best to describe what it sees in this matrix here as, let's say, my work community, people that I work with, that interact in a work scenario, right? As for my work community, it's very strong because it's mine or near my neighborhood. It's not for the entire graph, it's just for my neighborhood or some neighborhood of the users. And then we have this individual here, which is also very strong in this community because we are here together, right? It makes sense. So these values, when you multiply, will be a large value. It means that we have a link, we have a strong link, right? And that's what is, when we add to the other part, will give us a strong value here. Now, in my family community, this person is not in my family community, right? So in my family community, I'm very strong, but other people that I relate to may not be as strong. But in the end, if I sum these two values, then I get a large value. And my embedding will be related to all these coordinates. It's interesting, but if you think about, this is very egocentric, right? I'm just talking about myself. But this is for the entire matrix, for the entire network. So there will be other communities, right? Other latent representations of other people that I will be strongly there or very weakly there. Okay? So this is the mathematical definition. I put this, don't worry, I'm not going to go into the details, so that when you download the slides, you can run this and understand how, let's say, SVD works. I have two latent representations, and for this is a Facebook EgoNet. And if you run this, you realize some of the students doing my project are doing this, right? They're not familiar with this. So you realize that there are two communities that are very different, like kind of work people and the family parts of this individual that we are looking at, individual EgoNet. And they are in the latent representation, you see that some people, each point here is a person, and a lot of the people are represented strongly on one thing or the other thing, very few are both. Okay? It's kind of your work friends that are very close to you, like in terms of friendship, let's say. Okay. Now, I talked about characteristics. So how do you add characteristics to your network, right? I just described two, like user with another user or user and product. You want to add more things. You want to add their age. You want to add the time that something happened. You want to add, let's say, the time that we communicate. You want to add the words that we communicate with. You want to add many other things. So adding node and edge covariance is generally easy, and the folks doing my project probably may disagree a bit. But once you understand how it works, it's quite simple in reality. There are methods like Rascal, which is what Google uses for its, or used. I don't know if they're still used now with the neural network craze, for its knowledge graph. So when you did search on something, a lot of these results are related to this type of method. So the idea is just a generalization of what I just described, really. You have users, and let's say time. So it will represent how users are related over time. Or if this is age, would be how users are related with respect to their age. So it's just another dimension. So you can add as many covariants as you want. So here is a three-dimensional matrix, which we call tensor. We can have a four-dimensional array, which is actually the better proper term to describe it. 4, 5, 6, 10, 11, it doesn't matter. So for each dimension, you get one of these vectors. And you can get multiple vectors depending how many latent factors you want, or how big is the embedding that you are interested to represent. So all of these need to be together, right? So we have, so for this specific, let's say time, you would have a specific point in time where the values are large, and that represents that this matrix, this representation here is a matrix that happens during that time. If that makes sense. So think about it. I know that going from matrix to tensor seems weird, but it's actually quite easy to understand. Another thing that you can do, which I highly recommend if you're really interested in understanding how these models work and you want to better control what you are getting at the end, is to go to a full Bayesian probabilistic model. Because you can add as many covariates as you want, and you can do whatever you want. So Tina was talking a little bit about Bayesian methods, and also my work that Connie was talking about trajectory is also a Bayesian parametric method. So all of these that we have done in the past actually can be all interpreted as different types of Bayesian methods that have different assumptions, okay? So this is not a black box. We understand why this works and when this doesn't work. It's not a black box. It's a black box if you don't understand, but it's not a black box. It's not. We understand exactly why it works and when it doesn't work. Unlike deep learning, which we don't do. So you probably have heard of word-to-vec type embeddings. So you want to embed words, right, according with respect to the place in their sentence, with the location in the sentence. As I'm not a native speaker, Shakespeare sometimes is a bit daunting to me, and I don't understand what the sentences mean. Maybe you do, but if you don't, that's okay, because as a computer scientist, I don't care. Okay, so what I'll say is like, I want to know the relationship between women and husband, man and wife, right? So here we have man, we have wife, we have woman and husband. And I want to understand this relationship. So what I'll do, actually this idea came earlier than the word-to-vec paper, was named the Latent Markov Embedding. But they didn't have this really cool application. They are doing kind of song prediction. And then was rediscovered later and called word-to-vec, and they have very cool graphs. So it's interesting that in science sometimes you do something first and someone else does something later, and then they get more recognition. But here I'm just saying the main difference is that the word-to-vec paper paid more attention to the composition of latent vectors in the space, so it's actually paid more attention to the application rather than the first paper was more about predicting the outcomes. So let me explain how this works. So you have this husband, woman in a sentence. In another sentence, have man and wife. Then we'll have one of the ways of dealing with this is the conditional bag of words assumption, which they call the paper skip-gram. All the words are independent given the target word. So I put all some things that are close to woman in the sentence. I'll put them all and I say, I want to understand what's the probability of seeing the word bring if I have the word woman near. So what's the probability that I see the word bring near the word woman in a sentence, okay? That's what I'm trying to model. Then I'll do this. So one important thing is that you consider that given the woman, all the words in the sentence are conditionally independent. So they appear randomly, as if they were drawn from some distribution, which is this probability. Once you do this, you'll see that in a lot of sentences you see woman, husband, but you see very little woman constant. So you predict a higher probability that woman is related to husband than woman is related to constant. So the same thing that you do here for man and wife. Interestingly, the way that it works is very, very, very similar to the way that I just described, this latent decomposition that I described earlier. The only difference is that instead of just using the value that you're getting, we want to use an exponential over the value that I get. Okay, so that's the difference, really the difference. And then what I'll do is I'll try to normalize this exponential. So I get a value here in the decomposition, right? I multiply these two, I multiply the latent representations, I sum them, I pass an exponential, and then I normalize by all the possible words. So woman to husband, we do this, we sum over all the latent factors here, and then pass an exponential, and then divide by all possible words that the woman has nearby. This normalization gives us a probability, because exponential makes sure that this thing is positive. So these values here can be negative or positive, right? but the interpretation is the same that we had before. So we have still an embedding of woman as a conditional word. So if you have the word woman, it has some representation, okay? Maybe in Shakespeare's world, women means something evil, right? Or I don't know. But it could be, or something that is a queen, or some type of representation in this embedding here, right? So inductive embedding. Now, if we look at the embedding of the words, then if we project, let's say, if I have a rank 3 representation of this, right? Rank 3 means I have one more factor, so I have 3 dimensions for the word woman. I would see something like this. If I project the points wife, woman, husband, and man, I would see points in this 3-dimensional space. So the word would be embedded in this 3-dimensional space. Okay so far? Good? Okay. So how can you use this for networks? Here is the trick. So problem is, how do you represent a network in terms of these conditional probabilities? Right? What's a probability that if I see node V1, I'll see node V2, I should output or see node V2. If I see node V1, that's a probability that I see node V6. It's kind of a strange way of describing things, but this is what it is. This is what the math is that works for these methods. Okay, so you have to describe this as a word, this vertex as a word, and then the vertices that are nearby, whatever nearby means, as words in the same sentence. Okay? So note that for one example, for instance, is to say that nodes that correlate with node V1 are nodes that if you do a short random walk, you reach those nodes. What's the probability of reaching node 2 if I do a short random walk starting at node V1? This is one example, right? So we want to capture these probabilities. And once we capture these probabilities, we can embed these nodes into this latent representation, just as we did with words. So in the last 3 years, there is a lot of work on this. Why? Because there are so many possible ways of representing a network in terms of these sentences, right? Different vertices that you see given a node. Deep walk, node to vec, path to vec, meta to vec, subgraph to vec, struct to vec. They are still, I'm sure that if you go on archive today, you'll find another 3 papers that are not even here. So all of these works are using the standard word to vec under the hood, so everything that I just described is exactly what they are using. The difference is just what they are considered to be the sentence, right? The neighborhood of V1s. Okay. Now, what is interesting about this is that think about real tests and fake tests. I like to call fake tests. If you have a better name, please let me know. So the fake test is what in a lot of the papers we have to do because we don't have good data sets at all. So the fake task is this. I will give you a graph, and I say, well, produce an embedding that makes sense, and tell me that your embedding is good. And machine learning, what we mean by good is that you can predict something. But I gave you the graph already, and what are you going to predict? So what you generally do is you say, okay, I'll remove some of the links randomly. In the node to vec paper, they removed 50% of the links randomly. Well, it's not random because they make sure that the graph was connected. Not random. But generally, you would remove things randomly, and then you do your embedding, and then you see if you can predict back those links that you removed. Right? If you have a very, very high accuracy, meaning that the links that are likely, that you predict that are likely to exist, are mostly just the links that you removed, then you're supposedly doing a good job. Okay? So here, you can measure with the area under the ROC curve. It's just a metric of classifier accuracy, so you remove the links and you predict the same number of links back, and you see how many of them you got right. Kind of like that. So if we get 1.0, which would be here, you get perfect predictions, and 0.5 is random, okay? So you're just randomly predicting things. It's not a very useful classifier. As you can see, so I don't know if you can see this well, but here is how much of the graph we have removed, and here is the AUC of node2vec, and it seems to be very robust to different, from 40% removing 40% of the links to removing 90% of the links. Remember, not random, you have to make the graph still connected. There are some interesting things because you seem to get better. No, sorry. No, this is removing 60% and this is removing just 10%. So you can see that the accuracy is about 90%. The AUC is about 0.9. And this is the same task that they have in their paper, which I call fake task because it's not really a prediction, just removing things. If you have a dynamic graph, then you can make a real prediction, right? You can predict whether the link is there or not. So in the real task, let's say the BLP is a graph that is available that you can just try the same. It's hard to obtain this type of data, right? Dynamic data for social networks, so we don't usually do that, but let's try the same method on the BLP, and what you get is something like 0.6, which is much closer to random than you got, right, with the fake task. So in a real task, it doesn't do as well, and I have a intern that is working on writing a workshop paper specifically on why that's the case. But the thing is that a lot of these embedding methods that I'm describing, node2vec and a lot of the others, it's unclear whether they are good in the real task. Yes?
What is? Can I ask you a clarification question?
Yes.
So when they remove links, so if I have a social network and
Right.
I'm representing it as an adjacency matrix, are they just removing ones or are they removing ones and zeros?
They are removing just ones.
Just one.
Yeah.
What is the difference between node2vec and edge2vec?
Node2vec is?
Because here you have this edge2vec. I mean, you have two lines, the blue and the red one, right?
Oh yeah, so sorry. So here is that I'm removing, so here are the different biases. One is I'm removing a node, and then we sample a node and then remove one of the neighbors randomly. And in the edge, we remove edges randomly.
But it's always node2vec.
Yeah, always node2vec, yeah. Okay, so that's that. Now, we can understand that this embeddings as a transductive learning method. So everything that I show here so far are transductive learning methods, right? So we are reasoning about specific examples. The embedding is my embedding, and when you embed if you look at my local neighborhood and node2vec and all these word2vec type methods, you are looking at things that you are given the data, right, and then you are creating a latent representation of the data that you have. You are not generalizing to things that you haven't seen yet. So the next part, I'll talk about deep learning for transductive and inductive learning. And now I will just, so it's not too hard, right? Because now I'm transitioning. It's not too different, but I want you to take 5 minutes to breathe a bit. So you're not overwhelmed. No, but you're not overwhelmed, you know, by the how much content you're absorbing.
Maybe you can take questions in the 5 minutes?
I could take questions in the 5 minutes if you guys want. Or you can just close your eyes and meditate. Think a little
Can I
bit.
ask you a question?
Yes.
So the question is as follows. For the work you were talking about with node2vec,
Right.
wouldn't a better experiment be that I have my original graph that they're removing the links and doing what you showed,
Right.
but then I would add some random noise to that graph in terms of edges and see
Right.
how it does. So I have this rewiring parameter in terms of rewiring the edges or adding new edges, and then to see when does my algorithm fall off the cliff.
Right, that's an interesting idea. So we added a little bit of noise when we did this experiment with the intern. It's semi-robust, of course. If you add too much noise, then it doesn't work as well. But I will say this, the main characteristic of why it works is that they are keeping the graph connected.
I see.
So it's not removing links at random. Some links are not removed because they're too important.
But did you do the same for DPLP? Did you make sure that the
Now the DPLP is just a real task. I give 2 years of data and I'm predicting the next
okay.
year.
Yeah, okay.
Yes.
So are those the links where if I were to remove them, the high sliding value of the adjacency matrix will plummet?
Yeah. Yes.
Was about the question earlier. Do you keep all the nodes? Or do you sometimes remove nodes completely?
No, we keep all the nodes. Because transductive learning doesn't work well. If you remove nodes, you get something very different.
So you couldn't basically say that, okay, in order to, predict this, there should be a node which is hidden from me.
Sorry, say that again?
Let's say I remove a node.
Yeah.
And the algorithm would be able to, say that there's a missing one.
Oh, no. These are not missing node algorithms. They're all missing links. Are you ready for deep learning?
Sure.
Yes? Okay. No, let's go. Claudia doesn't want me to stop. I don't want. So we will talk what's deep learning. So most of what you hear about the discriminative models, I will not talk about generative models, okay? It refers to a deep architecture where you have one or more hidden layers. So I will explain what these hidden layers are. It's actually quite simple. So these hidden layers represent this hidden embedding. Remember that I talked about embeddings, like this idea of having some hidden variable that describes the behavior or describes the position of the user or what the user is like. So you're also creating hidden variables in this type of methods, okay? And the output layer is something that we want to predict. So you're given an input. This thing is a function that we are trying to learn, and we apply this function to predict an output. That's what it is. Okay, so a little bit of details, the way it works. So let's say that you have the digit number 2, and these are pixels. And let's say I have just 2 pixels to represent the number 2. So I have pixel 1, pixel 2, and this can be 1 or 0, 1 or 0. This one here is just a bias that you have to always put. If you don't put, it won't work well. So what we're trying to learn is this weight. So we multiply this value by these weights. And then we sum all of them, so there are weights for all of this input here. We sum all of them, like we did before, right? We multiply by some value. We pass by a nonlinear function. And then this will give us a representation of these things according to these weights through this function. So let's say if this is a logistic function, then this value here will be something between 0 and 1. And then this is the first hidden layer. So this will be my embedding now. And from the embedding, I have other weights that will sum and will pass through another nonlinear function, and that I'll get an output. For instance, if the nonlinear function is a logistic function, then I get something like the end value is you can interpret as a probability of something being true. For instance, there would be the probability that the digit is odd or the digit here that I input is even. So what you do is you give x, you give the final output, and then you try to learn this mapping, right? That best preserves that takes you from the input to the output. And in the end, you can interpret this value because the value between 0 and 1 as a probability of the input being 1. And all you're trying to do is to learn these weights here. These weights to do this mapping. Okay? This is what it is. So we'll care now about this embedding, okay? So this representation here. Now, let me tell you something about deep learning generally. That's very interesting, but also problematic when you're working with networks. There are tasks that it does really, really well. It does really well, these tasks. You probably heard about it, right? Video image recognition, text recognition, speech recognition, extremely well. What is common to all these tasks? What is the commonality of all these tasks? Yes?
Lots of data.
Not quite. Yes and no. Like you can do with not as much data actually. Yes.
Many dimensions.
Many
Many dimensions.
dimensions. But speech has only one, right? So yes.
Neighborhood is important.
Sorry.
Like the neighborhood is important at one specific point.
Neighborhood is important. Well, in speech, they don't really have a neighbor. Yes.
A lot of noise.
A lot of noise. There is noise. Yes. It would be better if there were no noise, right? So, okay.
You need
Context.
Context.
Yeah.
Almost. But of course, all that you are saying is true, or partially, right? But I have a relationship that I want to show you. All of these things have a very simple canonical orientation that I give to the learning method, right? Left to right, up and down. You train a neural network on this, and then you invert the image, down, up. It doesn't work. It doesn't work as well. Okay? Same thing with text, right? There is an orientation left to right. Speech, past and future, there is always a canonical orientation. So the methods work really well if you have a very easy or a very well-defined canonical orientation. And one of the problems with deep learning that a lot of researchers are trying to solve is how do you make sure that if the camera is tilted, you still don't crash your car, right? And there are new methods to do this, but it's not trivial. It's not something that can be done with the vanilla methods.
If you train the network with the same image but with different orientations.
You're just so what if you train the network with the same image and different orientation? That's what is done in most of the practical applications. They get the image, the car, and they rotate the car a bit. So to give different training examples. And now you can, if the car is rotated a bit, you're okay because you've seen this before.
Does it work?
Huh?
Does it work?
In practice, it works fine. But I'll give you a type of data that it doesn't have a very easy canonical representation. So when we are trying to learn these representations, and learning representations is about you get this input, and you're trying to learn this embedding, right? So you're trying to learn how to represent this thing in this latent space, in this embedding space. What about this? What's a canonical representation that I can give to this graph? My question is this. Think about these two graphs. Are these two graphs identical? Can you tell me? Meaning, like, are they in computer science, I guess in math also, we would say isomorphic, right? Can I remap, can I relabel these nodes such that I get exactly the same graph back? Yes? Yes? But now you solve one problem, right? How do you represent this in a way that is always consistent to the neural network? That's the hard problem. For a small graph, yes, okay. Imagine a 100,000 node graph. What do you do, right? So any solution that we have must come from some notion of canonical orientation for these graphs, right? We have to say these things are isomorphic, and I'm going to represent them the same way every time you see this as training examples. This is computationally expensive if we'll have to do multiple times and the graphs are reasonably large. Actually, Babai, there is very active IRF research now because Babai came with a polylog algorithm, which is very nice. Sub-exponential algorithm now, sub-exponential. So how do you do transductive learning with deep learning? What you can do is, well, you have to have some kind of canonical representation, right? So I'm here, and then I have some kind of order that I have to give the nodes to the input layer to get the output. And the output, just like word to vec, would be me. I am the output, okay? My node ID, let's say, is the output. And I give node IDs as input to this neural network. Now, how do you order this thing? Well, it's again the same problem with node to vec, right? Or word to vec. You have to find some way of representing this thing. The problem here is also that you have to find some way that is consistent. So if I gave you this same representation again, you would do the same thing. There are challenges because these input layers are fixed size. Network neighborhoods are different sizes, so you have to find a way to cut down if you have too large of a neighborhood. And there is actually no clear ordering of the neighbors, right? It's not clear how you should order the neighbors. Different orders will give different results. So you can write many papers on this. But the question is, how can deep learning then do inductive learning? Right? Transductive learning is harder here because you have to have this kind of ordering, which makes it even harder than before. Of course, you can pad, you can add things, but it's not ideal. The matrix factorization has better solutions than this. So one way of doing inductive learning would be, instead of putting the node IDs, you output, let's say, their colors, right? Some features about the nodes in an ordering that is canonical, meaning you get the same ordering if I give you some isomorphic graph. And then you try to predict my characteristic, okay, my label. I'm blue node, you give me my neighbors or some part of my neighbors, not all of them. And then you learn a function that will map my neighborhood characteristic to my characteristic. And once you do this, you can apply this in other parts of the network, right? You can also learn other labels. If you see the same labels, now you can predict my color. Okay? So it works very well if you have a task that has a canonical ordering. For instance, Tina's task of finding rows, right? Rows have a canonical order, degree have a canonical ordering. So my degree is something that can be represented here as a number, right? A feature, I put a color, but it could be a number like my degree. It could be my between centrality. You can find many different features that you can represent in this input layer, okay? And then you get an output that is something about me, my role or my characteristic or something. But Tina uses magic factorization rather than deep learning, but I'm sure that you can also use something similar like deep learning. But without a specific task in mind, right, where you can encode this thing as features or as scholars or as characteristics of the node in the neighborhood, then you have the same issues as you had before. The network is of different sizes. There's no clear ordering of the neighbors. Does that make sense? So how do we solve this problem? So this is where I stop here, and I was not talking about my work so far. Now I am going to talk about my work, I think. No, actually, no, I'm not talking about my work yet. I'm talking about previous work. So there is this idea of graph kernels, and the graph kernels is, because we like interesting words, kernel is just a representation of my neighborhood. Just a representation of my neighborhood, okay? So suppose that I break this down to subgraphs, so these works are talking about, there are many graph kernels. I'll say at least 20 papers on graph kernels. So if we break my neighborhood into subgraphs that I belong to, okay? And then let's say I put a histogram of the subgraph histogram, different 4-node subgraphs that I belong to. And then I get some characteristic about me as the function that I'm trying to learn. This will give me embeddings here, right, about my characteristic. So some latent representation of me in this latent space, the same way we did before. So let's say the input layer receives frequency of some subgraphs of radius b around the node. But because social networks have very short diameter, this becomes very quickly intractable. If you make b 5 on Facebook, then you're talking about collecting subgraphs of the entire world. And most people will have about the same features, right? So b is a parameter that is not easily, that really has to be very local. You cannot really say something about something that's very far. Another thing is that if you have a 100,000 node social network, you can have as many as 10 to the 20 subgraphs. Of course, if the network is sparse, it's way less, but it's still, this is a very large number. Okay, so the number of 4 node subgraphs will be 100,000 choose 4 possible. This is a very large number. So it's very high cost to capture complex patterns like larger subgraphs. If you decide to do 5. So Tina was talking about triangles, right? Triangles are hard to count. I'm talking about 4, 5, 6, right? It's really, like this is really hard. You cannot interpret the learned neural network parameters because you don't understand what this thing, trust me, I've tried. So you don't really, it's hard to understand what these weights are saying, what the latent embedding is telling you. It's harder. So what I want to do is to address these issues, all these issues that this also covered. So what we did, which is work that is just came up, we just finished, and we are putting an archive very soon. We are solving these interpretability, scalability, and canonical representation problems at the same time. And the idea is to propose a neural network structure that is related to the graph structure. Actually, it's related to the high-order graph structure. And I'll define that soon. It's a data-driven network structure, so if you give me a network, I will construct a neural network that matches the kind of the patterns that you see on that network, but then that can be used for inductive learning, and I'll explain why. So the idea is that we could simplify this network by cutting some links, and by cutting these links, if they represent something, cutting the link represents something on the network structure, then you can interpret now what this, the existing links are. So the data will better structure the neural network hidden layers, and the data, the social network, will drive what is the input layer. Let me explain what I mean. So the idea is the subgraph pattern convolutional neural network, where I'm trying to predict a pattern, let's say something that will change in the future in this network. Either a link, node, the activity of all nodes, anything that you want to predict of a subgraph, we can predict. And what this is we look at, let's say we try to predict the 3-node subgraph, things about the 3-node subgraph. We will look at the patterns that k plus, so if we are trying to predict k minus 1 node subgraphs, let's say 3-node subgraphs, we will look at 4-node subgraphs that encompass those 3 nodes in the network, and just look at patterns. So we are looking at patterns in the network that contain this example here that we have. And all these patterns that contain this example are just telling me, if I saw this pattern in the data, right, what would be the probability that this event happens? But because we are interested in constructing a neural network, deeper neural network, I'm not just describing what are the frequency of the subgraph patterns that I'm seeing from the data, but rather this will be a latent embedding. And around this subgraph here, I will look at, if you think about the high order network, so the network that if I replace one node here with another node, what would be the subgraph patterns that I would see in my data? Okay, so I have, let's say, this node is yellow, this is blue, this is red, and I add a green node, and if I replace any of these nodes with another node, I would have different patterns, okay? When I replace the node, I replace the nodes that are connected, right? So if this is connected to another node, then I replace this node by the other node, and I get patterns of subgraph patterns of that specific neighborhood. So the idea is just to describe this network as subgraph neighborhoods, a frequency of subgraph neighborhoods of different patterns that you see. And once you stack them all, what you get is a latent representation of where you are embedded and what are all the patterns that are around you. Okay? And those patterns can now predict what will be the evolution of this group. Not only you, but like a few of your friends. Okay? So to train this model, we need the k-node subgraphs in a very large graph. And so I did previous work on MCMC methods to sample a very large graph, 4-node subgraphs, a very large graph. So we don't need to break the whole graph down to 4-node subgraphs. We get very few examples. So few that in 4 minutes we can do this, we can learn this model in a 100,000 node subgraph. Sorry, 100,000 node graph with patterns of size 4. Because what we see is that this type of learning is so informative about the predictive power of what it will do in the future that we just need, let's say, 1,000 examples. You give me 1,000 examples, and then it's enough for me to predict the neighborhood of anybody else in the graph, or even other graphs. So what I think in this context here, I didn't describe the technique in too much detail because there is a lot more to describe. But what I want, if there is a take-home message for this technique is this. Think about the DBLP, right? We are predicting whether an author in the test data will publish at a given value for the first time. We never saw a publish at that value. And a given topic that we never saw this author publish before. Together. We want to predict both links together. So the link that we're trying to predict is author, topic, author, venue. Together, jointly, in the subgraph, right? In this 3-node subgraph, vertex, venue, topic, and author. Not one link, we're predicting subgraph properties. What is interesting about this neural network structure is that if I look at what the neural network thinks is a predictive property of a subgraph around me, around the author, the topic, and the venue, it says that if there is a topic that is connected to the topic that you are trying to predict, and that topic appeared on the venue that you could publish, then you're very likely, so this value here means that you're very likely to have a link in the future. Okay? For instance, if Alice has published in network science, and network science is related to deep learning, and AAAI has papers on deep learning, but not on network science, then Alice is likely to publish on deep learning at AAAI next year. So it learns this type of patterns. On the other hand, it predicts very negatively correlated that if I publish with an author, let's say Bob published at KDD on biology and on biology, okay? Bob published at KDD and on biology. KDD never had papers on biology, and Alice and Bob collaborated in the past. But she never published in biology or KDD, okay? So Alice is unlikely to publish in biology and KDD, these 2 links next year. So that's what the neural network is telling you with this structure. So now we can understand what patterns, right, are likely to emerge with the prediction test that you want, and why it's happening. So you understand why this is happening. And this is all in latent space, in this embedding space, okay? But the embedding space is not something that doesn't have an interpretation. We made sure that each part of the embedding space has an interpretation in terms of neighborhoods and subgraphs. So about this work, right? So we can predict any subgraph evolution pattern, jointly predict links in a group, jointly predict multiple label changes, predict group activity. And it's interesting because we can interpret these correlations between the network dynamics and the outcomes. So my lab and also Jennifer, we have a joint student working on this. We are looking for new applications. So if you have a cool application about predicting evolution and changes in subgraphs, come to us. The code is not yet online. As soon as we have the thing on archive, we will publish it. So take home, I think it's important to know what your problem is, right? If you're trying to do transductive learning, if you care about correlations rules, learn about correlations for the data that you have, or if you're trying to learn general correlation rules. So the work that I presented, we are trying to learn general correlation rules. What Tina was presenting, she's also trying to learn general rules, okay? Transductive learning cares only about neighborhoods, so you cannot generalize to other parts. Most embeddings are transductive, but you can talk about transfer learning. There are ways to get around that, but we can talk about that offline. Inductive learning, I think inductive learning is very interesting if you think about network-specific models, right? Not just applying whatever the new deep learning method is to your data. Just think about network-specific ways to represent in your deep learning structure. And with that, I am done. I'm open for questions. It doesn't have to be questions about my work, it can be questions generally about
Life.
life.
I have many dumb questions about this. I am a naive data mining, so I want to like to ask for your deep learning model, how can you represent the network data before you training the model?
How can you represent the
Network data, right? Because you have input and you try to predict the output.
Yeah.
So how you represent that into the data?
In my model or generally?
Both.
Both. Okay. So I think, as I said, it's representing a network as an input to a neural network is challenging because of this isomorphic problem, right? There is no canonical representation. If you don't represent isomorphic properties, then there is a problem. Like you won't learn well. Okay. So we have to have something input that is isomorphic. So if I give you an isomorphic graph, if I just change the order of these things, it has to be give the same values as input. So you should be able to do that. Okay, give consistent values as input. So any method that you do, you have to have this property. If you don't have this property, it's not going to.
So it's kind of like what you mentioned in the first section about latent latent model can be used for the.
Yeah. So those models, if you are interested in the theory, I highly recommend the papers of graph phones and especially Lova's paper on the graph exchangeability. It's a very theoretical, but it's really interesting. It explains why those methods that we were using all automatically represent these isomorphic graphs, right? Because the vertices are exchangeable. So those methods that I presented, they automatically take care of this. Deep learning does not. So you have to do something. If you don't do it, it won't work. I am telling you, if it works in your case, let me know. Okay? I doubt. It's very hard to learn without having some isomorphic representation.
And for the characteristic of the node, how can we represent? Because you have a node 2 vector, right?
Yeah.
That is only the structure of network.
Right.
Right. But how about the characteristic of the red dot? Because it's heterogeneous, so you have many features.
Whatever you want to choose. You can decide what you represent your neighborhood, how you represent your neighborhood, right? As long as it's canonical, it's always isomorphic graphs give the same thing, it will work somewhat. And the better representations will work better.
Because actually, it's really nice to see techniques that initially were developed in machine learning, numerical data and text data and images or videos now being applied to networks or even new techniques developed. I work with geographical data, so I was wondering if you're aware in the machine learning community of new techniques that are now developed to work with maps or to work with geographical data in general.
Yeah, so geographical data, I would say that the way that we would describe this is another big word in machine learning, manifold learning. And the idea is that, like Japan and here, well, Japan is, what's the farthest from here? I don't know. Japan, China and the US are the farthest, okay? So if you think about just distance-wise, right, you could go through the center of Earth, and then China may not look as far away. Or if you think about going through the sea, let's say Italy and the US, they don't look very far, but you can't really swim, right? So in geographic data, you have this notion of things that are easier to get to and things that are much harder. And it's not just a measure of distance, right? Euclidean distance. It's a measure of paths that you can take. So if you can represent this as a manifold or like a graph, then you can use this to then to represent your geographical data. And so there are a lot of work. There are a lot of works on using this idea of manifolds with Gaussian distributions, like things that are nearby are okay, right? But things that are geographically different, you have to say how easy it is to get from one place to the other. So I think manifold learning is the type of work that would apply really well to geographic. It has been applied to geographic data. No, you can.
No, it's fine.
How do you infer the optimal number of hidden layers and the size of each of them?
Right. So generally, what you do is to have to either create a fake task or have a real task in which you can measure your accuracy, and then you just do model selection over this validation data.
So empirically.
Yeah, you're doing it. Yeah. Oh, same question.
Here?
Maybe I should put on my. Yeah.
I have a question that goes back to basic logical thinking for the input layer in neural nets. As a sociolinguist, what I need to do now in my work is to set up combination of logical rules that people should use in generating content that is fed to the neural net in journalistic writing. And we have this dilemma whether if I instruct them to write basic sentences such as P implies Q, will it screw up the net if Q implies P?
No, if you use the same ordering. If you always use the same ordering.
Canonical ordering,
Yeah,
of course, but
canonical
if I move Q in P's place.
No, so what it will learn is that if whatever is here implies whatever is here. That's what it will learn. So you always have to put whatever you are trying to imply here and the preceding statement here. So it learns that this thing implies this.
Okay, regardless of what Q and P actually are.
Right, yeah.
Okay, thank you.
Okay, so I was still thinking about why this node-to-vec doesn't work. So have you, I mean,
No, I'm
you
not,
have, yeah, no,
that's
but
not
I
recorded.
thought-
Bruno is saying the node-to-vec doesn't
No,
work.
no,
I did not say that. I said that.
Let me try to understand. So I mean, if you look at DPLP, right, then also new nodes are coming into the system, right? So
Yes.
I mean, you for sure you have looked into what is the kind of cases where it fails, right? Is it kind of related to the degree of nodes for which you try to predict the new links? Is it related to any other properties of the nodes which potentially you can observe? I mean, since you look at scientists, you can kind of, I mean, you can explore the relationship between failing and other things which you can observe, right?
So far, we have not found an explanation to why.
But you looked into these
Yeah,
things
yeah, yeah.
and no correlation between.
There is mostly the problem of the DLP is that because it's all node-to-vec, like all learning methods, are transductive learning methods. So they're trying to embed you in a local neighborhood. And the BLP, because the dynamic graph is very sparse and disconnected, so it doesn't work well if you don't keep the graph connected. That's something that we know. Don't keep it connected. We never got it to work with whenever it's not connected.
That actually connects to my second question. The other thing I was wondering about when you talked about dimensionality reduction methods, right? You were saying, well, this is not a black box, we know that it works, and you can add as many dimensions as you want, and then you have the tensor, and it's still super cool and it works. So what about when it's super sparse? I mean, can you elaborate a bit on kind of, you know, conditions when it doesn't work, or what would be kind of, you know, things you would recommend to look at or
Right,
to
so,
do?
so if the method is sparse, I recommend that, so a lot of the methods, for instance, SVD, a lot of, some of the methods will treat no existing link as evidence that there is no connection, okay? There are more probabilistic methods that will treat a no existing link as nothing, will not say whether it's connected or disconnected. So those methods tend to work much better on sparse graphs. So there are methods to make a difference, right? Either if you don't see a link, could be evidence against a link, or it could be that you don't know. So in the model that you choose to represent this, you have to choose a model that treats the link the way that you want it to treat. If you use, for instance, SVD, it will treat a no existing link as evidence that there is no such link. But probabilistic methods don't have that problem in general.
Any other questions? If not,
Okay.
then let's thank Bruno again and